Okay, question 2. Part A. The molecular formulas of diatomic bromine, chlorine, fluorine, and iodine are written below. Circle the formula of the molecule that has the longest bond length. Justify your choice in terms of atomic structure. Okay, so to answer this question, we need to remember our periodic trends. So let's look at the periodic table. And in this case, we're looking at bond length. And bond length corresponds directly with atomic radius. The larger the radius, the larger the distance between the two bonded atoms. So on the periodic table, atomic radius increases as you move from right to left across the periodic table and from the top down. So our smallest radii are in the top right, and our largest are in the bottom left, generally speaking. And why is that? So elements in the same group or column, like the halogens that we're looking at, the radius increases as you move down the column because of the Pauli exclusion principle. Electrons are excluded from the region occupied by the core electrons. This forces electrons to more distant electron shells, resulting in an increase in size. So that's why, as you go from the top down in the periodic table, the atomic radius increases. So the elements that we're looking at are fluorine, chlorine, bromine, and iodine. And so iodine has the largest atomic radius. So individual iodine atoms are larger than any of those of bromine, chlorine, or fluorine. And so when bonded, the distance between the nuclei of I2 will be greater than bromine, chlorine, or fluorine. The iodine atoms are larger, so the distance between the two nuclei in bonded I2 will also be larger. Part B, using the data in the table above, write the balanced equation for the thermodynamically favorable reaction that will produce Br2 when the teacher combines two of the reagents. Justify the reaction is thermodynamically favorable by calculating the value of E0 for the reaction. Okay, so in this table we're given 3 possible half reactions to use and their standard cell potentials at 25 degrees Celsius. So the first thing we want is a balanced equation that will produce Br2 using 2 of the reagents above. So we know we definitely need this first reaction because it's the only one that has Br2 in it, and that's what we're aiming to make. And we know we need to reverse this because we want to produce Br2. So we'll write the reverse of that first half reaction. So 2Br minus goes to Br2 plus 2 electrons. And if we could look at these next 2 half reactions, it looks like either of them could be used to cancel out the 2 electrons and produce Br2. The important part is that we need a thermodynamically favorable reaction. And thermodynamically favorable means that E0 will be greater than 0. So it's spontaneous. It's thermodynamically favorable. So we know that this first reaction to produce Br2, we reversed the half reaction. So we will give the E0 for this reaction a negative sign because we reversed the half reaction. Now we need a second reaction and a second E0 that will give us, when combined, when added together, a positive E0. And we can pretty easily see that the only option is the chlorine reaction, because 1.36 is greater than 1.07, giving us a positive E0, as opposed to the iodine half reaction, that will only add 0.53 and won't give us a positive E0. So if we add the second reaction, And this is as written, so the E naught for the chlorine half reaction will be positive 1.36. So now let's combine the half reactions to give a balanced equation that will produce Br2. So our 2 electrons cancel on each side, and we are left with Cl2 plus 2 Br minus produces Br2 plus 2 Cl minus. There's our balanced equation. And our E naught is equal to minus 1.07 because we reversed the bromine half reaction, plus 1.36, and these are all in volts, 1.36 volts for the chlorine half reaction as written. That will give us a positive 0.29 volts as the E naught for this reaction. And because this E naught is greater than 0, we know that it is thermodynamically favorable. Br2 and Cl2 can react to form the compound BrCl. Part C. The boiling point of Br2 is 332 Kelvin, whereas the boiling point of BrCl is 278 Kelvin. Explain this difference in boiling point in terms of all the intermolecular forces present between molecules of each substance. They even underline each for you. And we're going to be looking at intermolecular forces because we're looking at boiling point. And of course, changes of phase have to do with intermolecular forces, not intramolecular forces, because phase changes don't rip apart the atoms in molecules, but they do change how closely packed molecules are, which is related to the strength of the intermolecular forces acting between the molecules. So let's first look at the intermolecular forces present in Br2 and Cl2 individually before comparing the relative strengths of these. So Br2 is a nonpolar, so it only has temporary dipoles that ever exist. And so that would only produce London dispersion forces. There's no permanent dipole in Br2. Both atoms are identical, so there's only possibly temporary dipoles that would be produced, and so the only intermolecular force would be London dispersion forces. BrCl, the bromine and chlorine atoms in BrCl aren't identical in terms of size, electronegativity. We'll have some small permanent dipoles in BrCl, and so that'll give us some dipole intermolecular forces at work. But we also have London dispersion forces as well, because London forces act between all molecules and atoms, so those are present here as well. So those are the intermolecular forces present in Br2 and BrCl2. Now we need to look at the difference in boiling point. So Br2 has 332 K and BrCl has 278 K. So initially you might think, well, BrCl, bromine monochloride, has 2 intermolecular forces at work, and dipole-dipole forces are generally stronger than London forces. But based on these numbers, we can say that Br2 has stronger London forces than both of the intermolecular forces present in bromine monochloride. The higher boiling point of Br2 shows that the intermolecular forces in Br2 are stronger than the combination of all of the intermolecular forces in BrCl, right? Because boiling point has everything to do with the strength of the intermolecular forces at work. And the London forces, so the stronger London forces in Br2, is dependent on the polarizability of the molecule. So the Br2 has stronger London forces, it has greater polarizability. We can deduce that because of the greater boiling point of Br2. Okay, part D. So we have a decomposition reaction of bromine monochloride into Br2 and Cl2. We're given the delta H of the reaction, and we are told that a 0.100 mole sample of pure BrCl gas is placed in a previously evacuated rigid 2.00 liter container at 298 K. And eventually the system reaches equilibrium according to the reaction. And we want to calculate the pressure in the container before equilibrium is established. Okay, this line of information is given to us as the situation before equilibrium is reached. So we have N, our number of moles is 0.100 moles, our volume is 2.0 liters, and our temperature is 298 K. We have our ideal gas equation, PV equals nRT, looking for P, so we'll divide the right side by V, and based on the units that we're working with, we know that we're going to be using the 0.0821 liter atmosphere per mole Kelvin gas constant. Okay, so let's plug everything in. Pressure is equal to 0.100 moles times 0.0821 liter atmosphere per mole Kelvin times 298 K, all divided by the volume, which is 2.00 liters. Put that in our calculator and we get a pressure of 1.22 atmospheres. So part E we'll do up here. Write the expression for the equilibrium constant, KEQ, for the decomposition of BrCl. So we have the decomposition balanced equation up here. So we know on this left side we'll consider these the reactants, and on the right side we'll consider these the products, because we start with bromine monochloride and it decomposes into the products. So the equilibrium constant, on the equations page we're given a concentration-based and a pressure-based equilibrium constant equations. Here we're going to write out the pressure-based equilibrium constant. So KEQ is equal to, so the pressures of the products multiplied together over the pressure of the reactants. So products, we have pressure of Br2 times the pressure of the other product, Cl2, divided by the pressure of the reactant, which is BrCl. Don't forget to bring that up to the exponent that is the coefficient in the balanced equation. So in the balanced equation we have a 2 in front of BrCl2, so that will be our exponent in the equilibrium constant equation. Likewise, we could replace all of these pressures with molar concentrations, with the exponent in the same place as well. Okay, part F. Okay, so now the system has reached equilibrium and 42% of the original BrCl has decomposed. So part F asks us to determine the value of the equilibrium constant for the decomposition reaction of BrCl at 298 K. Okay, so we know that we are at equilibrium because it tells us. So we're going to write out a Rice table to help us organize our thoughts. So in the R for reaction, we have our reaction that's further up in the questions, but we have 2BrCl is in equilibrium with Br2 plus Cl2. So for I, we're going to use our initial conditions. So we know from part D that initially, that is before equilibrium was established, all we had was BrCl gas. And we calculated the pressure of that gas to be 1.22. At that point, we had 0 of Br2 or Cl2. For the change, we can use our coefficient. There's a 2 in front of the BrCl2, so we have minus 2x. And there's a 1 in front of the two products, so we have plus 1x and plus 1x for each of those. So for equilibrium, we'll have to do a little bit of calculation because we're not told what the pressures are at equilibrium. But we are given information that 42% of the original BrCl has decomposed. So what does that tell us? That means that 58% of BrCl is still present. 42% has decomposed and 58% has not decomposed. So 0.58 times the original 1.22 atmospheres tells us the current pressure at equilibrium of the BrCl. So 0.58 times 1.22 gives us the pressure of BrCl at equilibrium, which is 0.71 atmospheres. So we'll put that in our Rice table, 0.71 for BrCl2. And so now we pretty much have this, this entire column filled in, and we can write a little equation to find out what x is. The initial pressure was 1.22. We have a change of minus 2x. That gives us 0.71 atmospheres. So we can easily calculate that x is equal to 0.26. 0 plus x gives us 0.26. 0 plus x gives us 0.26. We plug the equilibrium pressures into the equilibrium constant formula equation that we wrote up for part E. We will get that KEQ is equal to 0.26 times 0.26 divided by 0.71 squared, because the coefficient in front of BrCl, and we find that this gives us an equilibrium constant of 0.13. Now, we worked through this in terms of pressures, and you could also do it in terms of molar concentrations. So in a question like this, use a Rice table, keep your thoughts organized. Once you have a complete column filled in, you can write a little equation that will solve for x, and then you can find what the equilibrium pressures are for the remaining parts of the balanced equation. Okay, so part G, let's look at these bond energies. So we want to calculate the bond energy of a BrCl bond in kilojoules per mole using the delta H naught for the reaction, which they give us as 1.6 kilojoules per mole, and the information in the table. So we have 3 different bonds, Br-Br, Cl-Cl, and BrCl. We're given the bond energy in kilojoules per mole of these of the first 2, and we're asked to solve for the third. So they tell us that the delta H naught of reaction is equal to 1.6 kilojoules per mole. And what is the reaction that we're talking about? Well, it's the reaction that they gave us on the last page, that 2BrCl is in equilibrium with Br2 plus Cl2. So if we look at this reaction, it is a decomposition reaction. So BrCl is decomposing and forming Br2 and Cl2. So if we look at bonds broken and bonds formed, the bonds broken, that's the BrCl. How many? 2 BrCl bonds. Bonds formed, we have a Br and a Cl, one each. And the delta H naught of reaction is equal to, if we look at the equations page, we see that the delta H reaction is equal to sum of the delta H products minus the sum of delta H reactants. That's, if you don't remember, the more direct and relevant equation for this, the sum of the bond energy for broken bonds minus the sum of the bond energy for bonds formed. So obviously this second reaction is preferable if you can remember it, but you also can use the equation provided to kind of get to the same place if you can't remember during the test. So let's go on this side. So the delta H of reaction is 1.6 kilojoules per mole, and that's equal to the sum of the delta H of the products. So the products have bond energies of 193 and 243 kilojoules per mole, and we're subtracting the bond energy of two BrCl bonds. So if we work through this, we'll get a negative 434 kilojoules per mole is equal to negative 2 bond energy for BrCl, and we find that BrCl bond energy is equal to 219 kilojoules per mole. Likewise, you can use this equation, and you'll have the negatives will be in slightly different place. You'll have the bonds broken minus the bonds formed. The ordering will be slightly different, but what they're looking for here is just the correct calculation for the bond energy. And so if you're able to get 219 kilojoules per mole using either equation, you'll get the point.